Hello everyone. We've now had enough practice with the discrete Fourier transform that I'm ready to formalize something that maybe you've intuited going on in the background, but I want to say explicitly what's going on. And we're going to learn something called the inverse discrete Fourier transform, so it's going the other way. If I give you these Fourier coefficients, or the result of the probe signals, it's how do we go back? And actually, there's a very fast algorithm to do this, and it will allow us to do the resay beats over again really, really fast. So the Michael Jackson tune will be able to do it in a split second. And I feel a bit bad that even the fast version that I gave you in the last homework was significantly slower than that, but we just didn't have the background for me to tell you the really nice trick for resay. But now we're going to do it. And so if you want to do resay moving forward, I'll show you the code to do it. All right? So, without further ado, let's just do a quick recap on the discrete Fourier transform. So if we have an analysis signal, x of n. So by this I mean I have a signal, I don't necessarily know what's in it. I call that my analysis signal. I'm trying to analyze it. And so we're shifting in this unit to computing things about signals that we don't necessarily know, so computing statistics. Whereas in the first unit we mostly synthesize signals from models that we had. Okay, but this Fourier tool is going to allow us to say things about a signal that is unknown. So we'll call this xn. We'll say that it has big N samples. Then remember what we do is we define the discrete Fourier transform by taking dot products with probe signals, which are sines and cosines that go through an integer number of periods over the interval of n samples. So in particular, we will define the cosine components as the following dot product. So I'll say the cosine component at index k is equal to the dot product, which is a sum over all the samples. So I'll say n equals 0 to big N minus 1, assuming that we're 0 indexed, of the dot product of the analysis signal. So the element-wise product of the analysis signal with the probe signal, which is a pure cosine. And the frequency here is, as I said, it goes through an integer number of periods over the interval. And so for index k, it's supposed to go through k periods over the interval. So we would make the frequency, if you check it, it should be k over n times little n, which is my time index. And so yeah, if you check this, if I go through n samples, this will plug in big N for my time here, and so you'll get 2 pi times k, and that's k cycles. Okay, so this goes through k cycles over that interval. Let me just rearrange this a bit. People normally write it just like k times little n over big N. Okay, so that's the cosine component for frequency k. So we put that probe signal of the cosine with k cycles through. And for the sine component, it's exactly the same, except I change the probe signal to a sine at that frequency. Okay? And this gives us, actually to make this explicit, I'll show you. I mean, these are really, we think of them as arrays in their own right. And so what we're doing is really this transformation where we start with our signal, xn, which is some analysis array, and we transform it into 2 other arrays, one for cosine and one for sine. Actually, each one of these has n over 2 samples, big N over 2. And so we end up with the same number of samples in each of these as we had in the original. So what's interesting is we're not losing any information, but what we're doing is we're transforming to a different set of coordinates, which are a little bit more informative given how we hear sound. So the frequency of sinusoids that are involved in an audio signal is very important to our perception. So this set of coefficients is going to be a lot more meaningful for us to analyze than the mess of the raw audio samples that we start with here. Okay? Just to remind you, we did a brute force implementation of this in class. This is an exercise that we did last Friday and continued a bit on on Monday. And so really just from the definition, you can implement this, what I would say is call a brute force implementation of the discrete Fourier transform, but it's fine for our purposes right now. And you literally just go through and you loop through those n over 2 frequencies, and you compute the dot products, so the sum of the element-wise products, with the probes of the sine and the probes of the cosine. Actually, I don't like the way that's coded. Let's change that code there. Okay. Cosine comes first, then sine. Then we do that. Okay, cool. So that's nice. And just as a sanity check here, if we go ahead and let me set up, maybe I'll say, okay, I've got big N is equal to 100 samples. And let's, I'll put a couple of cosines in there. I'll say maybe X is equal to, so I should make my little N index. I'll say np.a range. And so I'm going to set up all the time indices of my original array here. So I'll say maybe X is equal to cosine of 2 pi. Let's say maybe I'll put in a frequency of 3 times little n over n. And maybe I'll say X plus equals np dot sine 2 pi times maybe 5 times little n over n. And so if I were to run this little DFT thing here on X, and I were to go ahead and plot, maybe I'll just say the first 10 samples of the cosine component. Well, I should probably import an numpy first, yes. Okay. So if I plot the first 10 samples of the cosine component, I definitely see that it lights up when k is equal to 3, which is great, so I see that. If I go ahead and I plot the first 10 samples of the sine, so let me make 2 plots here actually. So we got our cosine component, and then we're going to plot our sine component over here. Whoops, S there. Okay, cool. And so then we see we get something that lights up at 5, so that's great. And as we discussed in class, if there's a phase shift, what happens is, so if I were to subtract, some number on the inside here and shift my signal over, what happens is the frequency will split. So here's, I shift the cosine with 5, or the sinusoid with 5 hertz over. It'll split between a sine and a cosine. So now I see I see a coefficient that's non-zero in the cosine component, and I see a coefficient that's non-zero in the sine component for 5. Okay, so that's just a good little review, but make sure you understand this stuff, because this is the foundation of everything we're going to be doing in this unit. All right, now we focused here on going, what I would say, in the forward direction here, where we shake out each cosine and sine component, but we can actually go backwards. And the equation is remarkably similar. So I'm going to be a little bit sloppy with some of the normalization here, but what I mean by that is I may not get the exact amplitude. I'll get the amplitude up to a scale, but we'll see the right idea here. It's because I don't want to open up a certain can of worms. But all right, so let me explain what the inverse is here. So what we have to do, it's probably easier for me to write in code first, honestly. So what I'm going to do is I'll just copy and paste this code here real quick, and I'll say get the inverse discrete Fourier transform. So the goal of this is given the cosine and the sine components, reconstruct the signal x in the time domain. So it's the opposite of what we did before. Before we said I'm giving, so we call this the time domain. I'm given an analysis signal in the time domain of this time series of samples, and I wanted to compute these cosine and these sine coefficients. Now I'm saying, okay, I don't know what this signal was in the time domain, but I'm going to give you these cosine and sine coefficients. Can you go back and show me what signal would have given rise to those sines and cosines? And so I'm going to pass along the cosines and the sines. And so what I'll do is I'm going to set up an array to hold the result, and I'm going to loop through, so I'll say maybe n freaks equals length of cosine. I'm going to loop through each frequency index now. And so I have these probes already. What I need to do now is set up each probe and add it on with whatever its coefficient was. So if I look at the cosine frequency at index k, whatever the coefficient of that one, it's proportional to the amplitude of the cosine that was in x. Okay, so I'm going backwards. I'm like, how much of this cosine was there? That's how much it was. And let me sample that cosine over all samples there. So I'm going to do a similar kind of thing. Actually, let me set up my, oops, I'll say, my little n again, which is my time index, is np to a range big N. So, okay, so here's my probe. And what I want to do, as I said, well, this is how much of that probe that you had. Let's add that on at every sample. So I do that for the cosine, and then I do that for the sine as well. And then I go ahead and return x here. So let's have a look and see. So supposedly here I had, if I were to plot the original signal, this is what it looked like. And then this was the discrete Fourier transform. So now I'm trying to go the other way. I'm saying, given I don't have this information up here, but I do have this information, can I go back and reconstruct this? So let's see if I can do it. So if I input here, so I've got my C and I've got my S, and then if I say x reconstructed is equal to get inverse discrete Fourier transform, let's look at what that looks like. So fig size equals 12.4. So we'll plot x reconstructed. And oops, I made a little mistake, which is this is supposed to be a sine, right? Okay, good. So let's just have a look. So there is the original signal, and here's the resulting signal. And you see, like I said, the amplitude's a little bit off. You can control for that. I'm happy to talk more about that. It goes back to those trig identities and realizing that what happens when you probe a signal with itself. You basically just have to divide these coefficients by n over 2, and then everything works out. Actually, I'll show you that real quick. So really what I'm saying is, in order for this to work properly, you're supposed to divide each coefficient by n over 2. Then you'll actually recover the original amplitude. There's different ways to normalize these things too. But anyway, now you see that this number is actually 1. That was an amplitude of 1 here. And if I were to change this, maybe I'll make this an amplitude of 2 just to show you the point. So I get a slightly different signal. So anyway, okay, fine. I won't pull any punches here. I'll say this is how you normalize. You're actually supposed to divide the coefficients by big N in order for the amplitudes to be correct here. Okay, so then we do that, and when we do the inverse discrete Fourier transform, we actually recover the original signal with the amplitude. So actually, to convince you of that, I'll plot these right on top of each other. So yeah, so the orange dotted line is the original signal, and then the blue is what I get after doing the inverse discrete Fourier transform. So I guess I'll write that as an equation real quick, mathematically, just for completeness here. And then I'll let that sink in. We'll pause for a second. And I'll have a video where I then explain how we apply this to reset. Okay. But anyway, so the equation here would be, I'm saying, okay, x at a sample n, I have to sum up over all frequencies the cosine component times the cosine probe plus the sine component times the sine probe. And that's it. So there's my equation, and yeah, maybe I'll just rearrange it again to make it a little more standard. K little n over big N. And there we have it. Okay, so that is the inverse discrete Fourier transform. So I'm able to see these little titles here. This is the forward discrete Fourier transform. And this is the inverse discrete Fourier transform. But you may be more comfortable looking at this in code. So just have a look at these methods here. This one we did in class. This one we certainly could have done in class. Actually, let me move the inverse discrete Fourier transform down there. Yeah, this one we certainly could have done in class, but in the interest of time, I did it for you. Just going backwards. All right. So we'll let that sink in, and then I'll talk about reset.